So, let's go.
Number 12 on the countdown, magnetars.
Right. So what's fascinating here is just the sheer overpowering force of that magnetism. A magnetar is basically the collapsed core of a dead, massive star, packed into a sphere that's only about 20 kilometers across.
Which is tiny on a cosmic scale, like the size of a city.
Yeah, exactly. And to understand the threat, think about Earth. Our magnetic field is a gentle 30 to 60 microteslas. It nudges compass needles. It gracefully deflects solar wind. But a magnetar, it generates a field of 10 to 100 billion teslas.
Wait, billion? That's what, 100 million times stronger than any magnet humans have ever engineered.
Easy.
But I want to dig into the mechanism here. Why does a strong magnetic field dissolve a human body? I mean, magnets attract metal, right? Not flesh and bone.
Well, it comes down to how your atoms are built at a fundamental level.
Yeah.
Under normal physics, the electromagnetic force between the nucleus of an atom and its electrons keeps the whole thing roughly spherical.
Okay.
But when you introduce a 100 billion Tesla magnetic field, you just completely overpower the atom's internal forces. The electron clouds around your atomic nuclei get squeezed, and they distort along the magnetic field lines. It physically stretches your normally spherical atoms into these long, thin cylinders.
So chemistry as we know it just stops working.
Completely. The complex molecules making up your proteins, your cell walls, your blood, they require atoms to fit together in very specific geometric shapes. When all your atoms are suddenly shaped like needles,
The puzzle pieces don't fit anymore?
right, the chemical bonds just dissolve. And to put the reach of that power in perspective, if you placed a magnetar halfway to the moon, its field would be strong enough to wipe the data off every single credit card on Earth.
That is incredible and genuinely terrifying. But, okay, if a dead star's core can warp the shape of an atom, what happens when a massive star collapses entirely and punches a literal hole in space-time?
Moving on to number 11.
Exactly. Quasars. Now, I have to push back a little on the common understanding here, because the golden rule of a black hole is that its gravity is so intense, not even light can escape, right? It's utterly dark.
Right, that's the classic definition.
So how does a quasar, which is driven by a supermassive black hole, become the single brightest object in reality?
It seems like a paradox, for sure, but it's actually a brilliant, terrifying demonstration of energy conversion. The black hole itself is, in fact, completely dark. But quasars exist mostly in the early chaotic universe where these black holes are just surrounded by an endless buffet of gas and dust.
So they're feeding.
Voraciously. And when that material gets pulled in, it doesn't just fall straight down. Because of the conservation of angular momentum, think of like a figure skater spinning faster. When they pull their arms in the gas spirals, it flattens out into this massive accretion disk.
Okay, so all this material is caught in a cosmic traffic jam, basically swirling the drain.
And that traffic jam is moving at a significant fraction of the speed of light. The inner layers of the disk are spinning much, much faster than the outer layers. This creates unimaginable friction.
Oh, so it's a friction burn.
A cosmic blowtorch.
Yeah.
The material is rubbing together so violently that the kinetic energy converts into intense heat. We're talking millions of degrees. It blasts out energy across the entire electromagnetic spectrum, so a single quasar can outshine hundreds of billions of stars combined, all from an area roughly the size of our solar system.
So it's not the black hole shining, it's the friction of a galaxy's worth of gas just screaming as it gets ripped apart.
Exactly. It sterilizes entire star systems in its path with lethal gamma radiation.
Which makes the next item in our sources, number 10, feel a little too close for comfort, because we don't have to look back to the early universe to find one of these monsters. We have a cosmic landlord right next door.
Sagittarius A star, sitting right at the center of the Milky Way.
Yeah, located 26,000 light years away from us, packing the mass of 4.3 million suns. But the good news for you, the listener, is that our landlord is currently starved. It's quiet.
It's quiet right now, yes. But black holes are opportunistic eaters.
Yeah.
In 2022, the Event Horizon Telescope actually captured an image of Sagittarius A star.
Which was a massive deal.
Huge, and we saw this glowing ring of superheated gas surrounding the dark shadow of the Singularity. It's a messy eater just waiting in the dark. If a wandering star or even a massive gas cloud strays too close to that ring, the black hole will rip it apart and create a temporary violent flare.
Okay, so Sagittarius A star is anchored in the center of the galaxy. Gravity acts as the ultimate tether holding it there, but the sources point out that sometimes that tether snaps. Which brings us to number 9, Rogue black holes.
These are wild.
How exactly does an object with millions of times the mass of our sun just get kicked out of its home?
Well, it requires an event of truly cosmic violence. See, galaxies are not static structures. They drift, and they frequently collide. When two galaxies merge, their central supermassive black holes inevitably sink toward the new center and start spiraling around each other.
Like a terrifying dance.
Right. And as they spin, they literally churn up the fabric of space-time itself, emitting massive ripples known as gravitational waves.
So it's like two massive ships spinning in a whirlpool, kicking up these huge wakes.
A very apt analogy. But here is the critical mechanism. If those two black holes have different masses or they're spinning at different angles, those gravitational waves are fired off asymmetrically. More energy radiates in one direction than the other.
Oh, I see. And every action has an equal and opposite reaction.
Exactly. This imbalance acts like a gigantic misfiring rocket thruster. It delivers a gravitational kick so powerful it can overcome the escape velocity of the entire galaxy.
Meaning, this newly merged black hole is literally shot into intergalactic space at thousands of kilometers per second.
And it's not just the supermassive ones. The sources note that stellar mass black holes, the smaller ones born from collapsing stars, can experience similar kicks from asymmetrical supernova explosions.
And here's where it gets really interesting for our local neighborhood. In 2022, astronomers actually confirmed a rogue stellar mass black hole just 5,000 light years away.
Just cruising through the Milky Way at 45 kilometers per second.
And it is perfectly stealthy.
Completely.
Right.
Because they emit no light, and if they aren't actively feeding on a disk of gas, they are invisible. Millions of them could be wandering the Milky Way right now like cosmic landmines.
Which obviously raises a huge question. If they are completely invisible, how do we know that specific one was moving at 45 kilometers per second?
That's thanks to a trick of physics called gravitational microlensing. Massive objects warp the fabric of space-time around them, right?
Right, like a bowling ball on a trampoline.
Exactly. So if a rogue black hole happens to drift perfectly between our telescopes in a distant background star, the black hole's gravity acts like a magnifying glass. It bends and focuses the star's light, making it temporarily appear much brighter.
So we don't actually see the black hole itself, we just see the warped magnification of the space it moves through.
That's the only warning we get.
Wow. Okay, so let's put you, the listener, into the ultimate theoretical nightmare here. Number 8 on our countdown. What happens if one of these invisible wanderers drifts through our solar system and you get caught in its gravitational pull? The boundary of no return, the event horizon.
The point where physics just says no.
Yeah. Let's talk about the mechanics of that perimeter. On Earth, we use rockets to overcome gravity. You need an escape velocity of about 7 miles per second to leave Earth's orbit.
Right, and the more massive and dense the object, the higher the escape velocity required to leave it. The defining feature of a black hole is that a massive amount of matter has been compressed into a space so incredibly small that the gravity around it scales toward infinity.
So at a certain distance from the center,
The escape velocity required to pull away matches the speed of light.
and since Einstein's theory of special relativity dictates that absolutely nothing in the universe can travel faster than light in a vacuum, that boundary becomes the absolute limit of reality.
We call that physical boundary the Schwarzschild radius.
Yeah.
Once you cross it, you aren't just trapped. The very geometry of space and time curves inward. All possible paths forward lead only to the center.
But the physical destruction starts before you even cross the line, right? Through a process astrophysicists very casually call spaghettification.
Yeah, funny name for a horrific way to go.
It's the ultimate stretching rack. Explain the mechanism behind that, because it's not just gravity pulling you, is it? It's about a gradient.
Precisely. Gravity follows an inverse square law, meaning its strength drops off exponentially with distance. Because a black hole is so incredibly dense, that gravitational gradient is razor sharp.
So if we were to drop you feet first toward a stellar mass black hole,
By the time I approach the event horizon, the gravitational pull on my feet is millions of times stronger than the pull on my head, which is just a couple of meters further away.
so your feet are accelerating violently faster than your torso.
Yes. That massive difference in force, the tidal force, literally stretches your body into a stream of subatomic particles, while simultaneously crushing you inward from the sides.
Good grief.
But the real mind bender is what happens to time from an outside perspective.
Right. If I was safely in a spaceship watching you fall in, I would never actually see you cross the threshold.
You wouldn't. This is due to time dilation. As I fall closer to the immense gravity of the event horizon, space-time stretches. The light reflecting off my body has to fight incredibly hard to climb out of that steep gravity well.
It's losing energy.
Exactly. As the light loses energy struggling against gravity, its wavelength stretches out, shifting into the red and infrared spectrum. To your eyes, my image would appear to slow down, freeze entirely at the very edge of the horizon, and slowly fade into imperceptibility.
You are just gone, cut off from our reality forever.
Yeah. But this raises an important question. We've talked about a single black hole dragging matter into the dark. What happens when whole galaxies are being dragged?
Oof. That brings us to number 7, the unseen forces pulling on us, the Great Attractor. We know that since the Big Bang, the universe has been expanding. On a grand scale, everything should be moving away from everything else. But astronomers found a massive, terrifying glitch in the movement of our own galaxy.
Yeah, the Milky Way, along with hundreds of thousands of neighboring galaxies, is speeding at 600 kilometers per second toward a specific region of space. It's roughly 150 to 250 million light years away.
And for decades, it was a complete mystery, right? Because it sits right in what astronomers call the zone of avoidance.
Which sounds like something from a sci-fi movie.
It really does, but it just means it's directly behind the thickest dust and starlight of the Milky Way center. We were being pulled toward a literal blind spot.
We have since used X-ray and radio telescopes to peer through that dust, and we found massive clusters of galaxies there. But the visible matter alone isn't nearly enough to explain the immense gravitational pull.
So what's doing the heavy lifting?
Most of that dragging force is driven by dark matter, an invisible scaffolding of mass that interacts with gravity but not light. It essentially proves that our entire galaxy is just a speck of dust caught in a massive, invisible cosmic current draining toward the center of the Laniakea supercluster.
But if the Great Attractor is an example of invisible local mass, number 6 on the countdown, dark flow, is where cosmology starts to crack entirely.
Oh, dark flow is where things get really uncomfortable.
Because we aren't just talking about local clusters anymore. Let's look at the cosmic microwave background, the ambient radiation left over from the Big Bang. If cosmic expansion is uniform, galaxy clusters across the universe should be drifting apart randomly. So how is it that massive galaxy clusters spanning billions of light years are all streaming in the exact same direction?
Toward the constellations of Centaurus and Vela at 2 million miles per hour.
Right. How is that possible?
Well, that phenomenon was discovered by the WMAP satellite in 2008, and it remains one of the most unsettling findings in astrophysics. When we calculate the mass of the entire observable universe, there is simply a massive deficit. There is not enough matter in our reality to cause a unified gravitational pull on that scale.
So wait, the mass required to drag us doesn't exist in our universe?
That's the leading hypothesis.
Yeah.
It points to the very first moments of the Big Bang during the period of rapid cosmic inflation. The theory suggests that unimaginably massive structures, maybe giant concentrations of matter or energy, were pushed completely outside our observable universe.
Wow.
Yeah, the space expanded faster than their light could travel, so we will never ever see them. But their gravitational influence doesn't rely on light. That gravity is still reaching back across the boundary of the observable universe, tilting the cosmic table and dragging entire sectors of our reality toward the dark edge.
An infinitely huge weight hiding just outside the walls of reality, tilting the floor we stand on. That is just bonkers.
Okay, so if there are regions outside the universe hoarding mass, what about the spaces inside the universe that are entirely missing it? That brings us to number 5, the terrifying emptiness of the cosmic voids. Specifically, the Eridanus supervoid.
Right, so when astronomers mapped that same cosmic microwave background we just mentioned, they found a region in the constellation Eridanus where the temperature suddenly drops by about 70 microkelvin.
Which doesn't sound like much.
In the highly uniform background of the universe, a cold spot that large is a screaming anomaly. The statistical chance of it forming randomly is about 1 in 2,000.
And in 2021, they found the culprit. An elongated, cigar-shaped void of absolute emptiness stretching 1.8 billion light-years wide. But I want to explore the mechanism here. How does empty space create a cold spot in the background radiation? It's driven by a phenomenon called the integrated Sachs-Wolf effect. So imagine light traveling through the universe as a marble rolling across a landscape. When it hits a void, it's like rolling into a massive, shallow valley. Normally, the marble rolls down, gains kinetic energy, and then uses that exact same energy to roll back up the other side, a net zero change.
But the universe isn't static, it's expanding.
Exactly the problem. While the photon of light is traveling through that billion light-year valley, the expansion of the universe is physically stretching the valley wider and shallower.
Oh, so the geography changes while it's inside.
Right. By the time the light is ready to climb out, the shape of the gravity well has changed. The light has to expend more energy to climb out than it gained falling in. For a photon, a loss of energy manifests as a drop in frequency, meaning it literally gets colder.
But the sources note that even a void 1.8 billion light years wide isn't big enough to fully explain the math of that temperature drop. There's still a missing piece to the Eridanus puzzle.
Which leaves room for some wild theories. Some physicists suggest it's a cosmic texture, literally a crack in the physical fabric of space-time.
And others propose an even wilder idea. It's a bruise, like a scar left over from when our expanding universe physically crashed into an entirely different parallel universe in the distant past.
It really highlights how much we still don't know. But, while the Eridanus supervoid breaks our physical models, number 4 on the list, the Boötes void breaks our psychological grasp of scale.
Discovered in 1981, it's a spherical region of nothingness, 330 million light-years across. Let me put that scale into perspective for you. Based on the average distribution of matter, a space that massive should hold roughly 2,000 galaxies. But it doesn't.
No, astronomers have found barely 60 lonely, isolated galaxies drifting inside it.
If we magically teleported the Milky Way to the dead center of the Boötes void, the night sky wouldn't just be missing a few stars. It would be a void of suffocating total blackness.
It looks as though a cosmic eraser was taken to a massive chunk of the universe. If an alien civilization evolved in one of those central 60 galaxies, the sheer distance between them and anything else would be insurmountable.
They wouldn't have even known other galaxies existed until they invented advanced optical telescopes in the 1960s.
They would have spent their entire history believing their galaxy was the only object in a pitch-black, infinite sea.
Which is so profoundly lonely. But it perfectly sets up our final descent. We've explored the voids where matter was erased. Now let's look at where the matter was hoarded. Number 3, TON 618.
We talked earlier about Sagittarius A star being 4.3 million solar masses. Well, 10.8 billion light-years away sits TON 618, a hyperluminous quasar. The mass of the black hole powering it is estimated to be between 40 and 66 billion times the mass of our sun.
66 billion suns. That is heavier than all the stars in the Milky Way combined, crushed into a single point.
Yeah, astrophysicists literally had to invent a new classification category for it. The ultramassive black hole.
Let's go back to that physical boundary we defined earlier, the Schwarzschild radius. Because the size of an event horizon scales directly with mass, TON 618's radius stretches for 1,300 astronomical units.
1 astronomical unit is the distance from the Earth to the Sun. Pluto is roughly 40 astronomical units out, so you could fit our entire solar system inside TON 618's event horizon dozens of times end to end, and it wouldn't even brush the edges.
It's incomprehensible.
Which naturally leads us to number 2. The singularity itself, what lies at the absolute bottom of a gravitational well that deep. Because the sources describe it as having infinite mass packed into zero volume. And honestly, that sounds less like physics and more like math, just throwing his hands up in defeat. That is precisely what it is. The singularity is where the 2 foundational pillars of modern physics, general relativity and quantum mechanics, violently crash into each other. General relativity describes gravity as the warping of space-time, and inside a black hole, it says the mass collapses to a single point of infinite density, creating infinite gravity.
But quantum mechanics, which governs the subatomic world, explicitly forbids infinite density, right? You cannot pack matter into zero volume due to the uncertainty principle.
And yet the black hole exists. The equations spit out infinities, which basically tells physicists our models are fundamentally broken at this scale. At the singularity, the concepts of where you are and when you are lose all meaning. Time and space literally swap properties.
It is a literal hole punched straight through the fabric of reality.
A hole in reality.
Which brings us to the ultimate extreme, the final breakdown, number 1 on our countdown. We've looked at the collapse of stars and the collapse of physics at a singularity, but what about the collapse of the entire universe? The cosmological horizon.
Right, so the universe was born 13.8 billion years ago. Because light has a finite speed, we can only see objects whose light has had enough time to reach us. Due to cosmic expansion, that boundary at the particle horizon is currently stretching about 46.5 billion light-years away in every direction.
But the universe isn't just expanding, that expansion is accelerating. The mysterious force we call dark energy is hitting the gas pedal.
Exactly. This creates the cosmic event horizon, located about 16 billion light years away. The space between us and galaxies beyond that point is physically stretching faster than the speed of light.
Think of it like a cosmic treadmill. If you run at 5 miles an hour on a treadmill moving backwards at 10 miles an hour, you are never going to reach the control panel. The light from those distant galaxies is trying to reach us, but the space it is traveling through is expanding faster than the light can cover the distance.
The devastating conclusion here is that right now, every single second, thousands of stars and distant galaxies are slipping over that cosmic event horizon.
Just winking out.
Yeah. The light they emit today will never, ever reach Earth. They are vanishing from our future reality. Billions of years from now, the expansion will be so rapid that every galaxy outside our local group will be pushed beyond the horizon.
The night sky will go entirely dark.
And any future observers will be trapped in an empty void, completely cut off from the rest of the cosmos.
So, what does all of this mean for you listening right now? We've talked about magnetic fields that dissolve chemistry, invisible rogue black holes, math-breaking singularities, and a universe that is fundamentally deleting its own history. It can feel deeply, deeply overwhelming.
Oh, absolutely.
But it shouldn't just induce dread. To me, it really highlights how profoundly lucky we are. Our daily lives exist in this tiny, incredibly precious bubble of stable, predictable physics. We are sheltered from the violent extremes of the broader cosmos.
It is a remarkable privilege, honestly, to exist in a neighborhood where atoms hold their shape, chemistry thrives, and the sky is still full of light. But, there is a final fascinating thought to take away from this expanding universe. We discussed how galaxies are quietly slipping over that cosmic event horizon, forever disappearing from our view.
Right, running on that impossible treadmill.
But the expansion of space is relative.
Yeah.
Consider this. Right now, at this exact second, an alien civilization in one of those distant, fading galaxies might be looking through their own telescopes, pointing them directly at the Milky Way.
Oh, wow.
To them, we're the ones being carried away by expanding space. To them, we're the ones whose light is stretching into infrared, freezing at the edge of the horizon and slipping silently into the dark.
So who is really disappearing? Are they leaving our reality, or are we fading from theirs? It brings us right back to that thin layer of ice we talked about at the start. Our foundation of localized physics is holding for now, but the abyss underneath is vast, violent, and full of mysteries we are only just beginning to map. Keep looking up and stay curious.